Using blueprints to prototype mechanics and systems is a common practice, but once you're done scripting, how do you go about translating them into C++, their more performant and functional sibling? In this tutorial, I will show you my method using multiple examples of different complexities. Also, to make sure I don't make any grammatical mistakes in my code, I will be using PVS-Studio, an optional static analyzer by Viva64, the sponsor of this video. Let's get started. First, we will work on a one-to-one translation, where there is no need to adapt the code and which is only a matter of knowing the corresponding functions in the C++ API. So let's start off simple and take a basic double jumping system as the first example, and go through the whole process of translating it into C++. This tutorial isn't about writing code along with me, but instead it's about understanding patterns of translation. However, if you want to follow along, here is the blueprint code. We'll begin by creating an input function called jump that will fire when the spacebar key is pressed. Now we can start building the function. The next step would be to add a do-an inside the function. But Unreal only comes with a pre-made do-an macro for blueprints, so we have to recreate it ourselves. For that, I will add an integer called jump counter that we have to set to 0 in the constructor. Now, every time the jump function is called, we have to increment it and make sure it never goes past 1. We can do that by checking if its value is less than or equal to 1 before the incrementation. Still inside this if statement, to simulate jumping, we can call launch character on the z-axis, just like we did in blueprints. To be more precise, we construct a vector with 500 units on the z-axis and override the z velocity to stop the player from building momentum. Technically, this should work just fine, but the counter never resets, so we need to create an onLanded function that sets it back to 0. So, to figure out how we can implement it, let's take a quick glance in the API, which tells us everything we need to know. Its parent is the character class, and its signature includes an fHitResult input. With these details, we can go in the header file of our character, paste the signature, and override it. Now, we can customize this function however we want, and in our case, we just have to set the counter back to 0. And that is how I would translate this double jumping system. Let's take a new example, in which, besides having to translate the code, we also have to adapt it. So in this case, let's try to translate a simple interaction system based on line traces that interact with whatever they hit. The first step is creating an input function just like we did before, so I will quickly get over that. Then, the first node we need to translate is the line trace node, which in C++ needs adaption, because it behaves slightly different from its blueprint version. So first, we compute the start and end positions of the line trace, as well as its other inputs, such as the collision query parameters and the hit result. Now we can fire the line trace by supplying the function with the hit result, start, and trace channel and collision parameters. But here's the catch. In C++, line traces return a boolean that represents if the hit was successful. This is the equivalent of the return value in blueprints. So, to use this properly, we can put it inside an if statement. Then, because we fed the function with a pointer to the hit result, this acts as a secondary output, precisely the out hit in the blueprint version. That's pretty much all the adapting we had to do. And from here on, it's just a matter of properly casting to your interactable class with a hit actor and calling the interact function. The takeaway is that some nodes are a number of code lines compiled into one single function. For instance, as we have just seen, line traces, which have a drastically different syntax than blueprints, that removes the commodity of having everything in one place. There may be some errors in this code, so let's check it using PVS-Studio, a static code analyzer. This is a quality control and bug detection tool, which can make writing proper code easy and convenient. You can see why this is useful. As game developers, we strive to avoid bugs and to write performant code for the sake of a smooth playing experience. If you want to give it a try on your own projects, check out the link in the description and use code Nitrogen for a 1-month trial. And while you're there, visit their YouTube channel as well. After it finished analyzing, we can see that there are no errors, so we can go on to the next step, which is about using workarounds. Sometimes, there is no straightforward way to adapt a piece of code, so we have to come up with creative solutions that may not seem obvious at first. In this piece of blueprint, which lets the player dash forward, there is such an example. Before translating this as well, let me know in the comments, which nodes do you think will need a workaround? We will once again go over creating a new input function and assigning it to an action binding. As well, let's create a can-boolean, which we set to true in the constructor. Now, the first part of the code is a simple one-to-one translation. Check if we can dash, then if that's true, set a boolean to false and launch the character 8000 units forward, excluding the z-axis and overriding both vertical and horizontal velocities. Then, after nearly a tenth of a second, we need to immediately stop the character. But question, how does one create a delay in C++? There's no explicit delay function. Instead, we can use a workaround and let a timer do the job. In blueprints, this is mostly used to repeatedly call a function every x seconds, but we can tell it not to loop. Although we can use anonymous functions, for the sake of simplicity, let's create two new functions, one for stopping the character and one for resetting the can-boolean to true. We will add their implementations in a bit, because first, we also have to create an ftimer handle, as well as to include the timer manager header in the C++ file. Then, back in the dash function, we can set a new timer by getting the world timer manager and calling setTimer, which requires our new timer handle, a function reference, in our case stop dash, after how long to call this function, practically the equivalent of the delay node, and a false boolean to prevent it from looping. Next, in the stop dash function, simply call stop movement immediately. This would be everything for the dashing itself, but we also have to reset the dash boolean. For that, we'll use another timer in stop dash of 3 seconds that calls the reset dash function. And that is how you work around not having an explicit delay function. PVS-Studio returns no error, so we are also done with this example. Though you should remember that these patterns won't always apply. Sometimes, adapting won't mean just understanding that the line trace function takes certain inputs and that it returns a boolean. And workarounds won't be as simple as using a non-obvious function like timers. But from my experience, more often than not, these 3 types will be useful guidelines when translating blueprints to C++. That's it for this tutorial. If you found it helpful, please leave a like and subscribe to keep up on any future uploads. Or consider becoming a patron and supporting me directly like these beautiful human beings. Avirama FM, Badr Al-Kahtani, Giovanni Pena, Golden Glowmaster, Realitats Verlast, and Waifu is Laifu. Thank you so much for watching. I will catch you in the next one. Cheers!